Swayam Prabha. Digital India. Educated India.
All right, let's get started. So, recall that we are discussing Simon's algorithm over Zn, and towards this, in the last lecture, we developed the theory about the quantum Fourier transform over Zn. Is that clear to everybody? Is there anything that you would like me to repeat? So, we went over it a little bit quickly. This was mainly because we spent a lot of time over QFT when we talked about it originally over Z2n, and at least algebraically there is only a little bit of change. So, we have gone over it a little quickly, but if in case something is not clear, please let me know as always. Okay, so now let's get started again. So here, remember, we are trying to understand, what is an efficient quantum algorithm for period finding. Okay, so given a periodic function, we want to figure out what is an efficient way to find the period of this function, and classically we expect this to take exponential time, but we hope to do much better here. Now, yes, in yesterday's class, there was a feedback that, we had ended the class with this discussion on why measuring, before applying the QFT does not help us. So, I am not sure if whoever wrote that is here now, but I wanted to say that let's talk about that, but let's first state the problem clearly and start developing the algorithm, and then when we come to it, we will discuss it, because it will be like jumping in the middle otherwise. Okay, so let's first of all, just state the question, right. So, last lecture we just talked about QFT, and now we will talk about what is the actual problem we are trying to solve and how to apply the QFT to that. So, this is a very, very important problem. Okay, this is the period finding problem. And here what you have is that you have a periodic function. So, let us say that this function goes from Zn to some set colors. Okay, so essentially what does this colors here indicate? I mean, it just means that this is an unstructured set. So, obviously we will not particularly care about, red, blue, green and other colors. It just indicates that this is an unstructured set. There is no algebraic structure that we can make use of over here. Okay. So, I have this function, and I have oracle access to this function, and the promise that I have is that the function is periodic. So, there is some S some non-zero S. It holds that f of x is equal to f of x plus s. Okay, and otherwise f values are distinct. So, basically if x and y do not differ, by a multiple of s, then f(x) is not equal to f(y). okay, and the goal is as before, to find S. Alright. So, this is the question. Is the question clear to everybody? Okay. So, this is what we want to do, and I do want to mention that so in order to solve factoring, period finding by itself will actually not be enough. What we need is something a little different, which is order finding. So, we want to find the order of an element in a group. We will come to that. So, what we will do is we will develop an algorithm for period finding, and we will see that this actually also works if the function is not exactly periodic, but almost periodic. We will see what that means, and this is going to help us when we think about factoring. So, we will show that what we need to do to solve factoring is find the order of an element in a group, and finding the order of that element will be like finding the period of an approximately periodic function. Okay, so let's come to that, but I just want to sort of tell us where we are going. So, this is our problem, okay, and so now what is our algorithm? So, the algorithm is very similar to the old Simon's algorithm that we have seen. Okay, and this is the context in which we have to discuss the real value of QFT. So, first of all, I'll just prepare the superposition state. Of inputs, right. So, this is basically 1 over root n summation of x over z n x. Okay, so this is just the superposition of all inputs. So, this part is sort of standard by now. Then we will attach some set of zeros to it, okay, to get 1 over root n x 0. The third thing is apply the function oracle. Okay, so now I will get 1 over root n summation x x f x. So far we kind of discussed even yesterday, okay, that this is sort of, these are the standard steps. So, normally when we apply the function oracle, we could apply it in two different ways, either this way or using the phase kickback, where the value of fx is encoded in the exponent of -1. Here this is going to be what will be useful for us. So, now good. So, what we discussed yesterday is that at this junction, right, if I measure my second register, if I measure this, then what happens? What happens is that you collapse to a given color, right. So, now you have measured f of x. So, if there are how many ever colors, red, blue, green, orange, whatever they are, when I do this measurement, I collapse to one fixed color, any one of them at random, okay. And what we discussed was that the input, this input register x, this will now collapse to a superposition of all values that map to this this color. So, yeah, so what we were saying was that once you collapse to a given color, the input register is going to have a superposition of all those inputs that map to that color, right. So, all those x's such that f of x is equal to whatever, let us say 0 or whatever color, your favorite fixed color. So, that means in particular that you will end up with things like some x0 plus x0 plus x plus x0 plus 2s and so on and so forth, right. If I measure the second set of registers, the first set of registers, the first register is going to contain these qubits in superposition. So, the question that we were asking yesterday was how should we proceed from here, and one of the suggestions from the class was that let me just measure the first register now. So, in that case I can hope to get some x0 plus ks. Basically when I measure a few times, the hope is to get different sort of values that are separated only by some multiple of s, and hopefully thereby to recover s. So, this was the idea that I had said, that the intuition is sort of very roughly correct, but it is important in the most, it is incorrect in the most important way. So, it is missing a subtlety which is actually at the heart of what is going on over here. And what is that subtlety? So, now I would like to ask you the same question from yesterday. So, if I just measure the second register and then just measure the first register, I will get some value. So, if I repeat this, can I use that to recover S? This is my question.
No, because again the next color might not be the same color.
Yeah, that is exactly right. So, it does not work, because in let us say that I get some value. So, let us say I measure and I get x0 plus 2s. Now, when I repeat this process, right, I won't get a multiple of s offset by the same x0, right. It will be some x0 prime or something, and this is just giving me sort of random values in the space, which is not going to help me to recover s. So, in order for me to recover s, what I actually need is to have my measurements give me some useful information about s, which is nevertheless independent of the color. So, this is what I was getting at the end of last class, that I have to make this process independent of color, and the QFT will make that happen. Okay, good. So, let us come back to this. So, what we were saying was that if we simply measure the input registers at this stage, we will not get something that we can use. So, therefore, we will sort of apply our our main powerful tool that we have, which is we want to apply the QFT. Okay. Apply QFT to the input registers. And then do some classical computation. So, we'll get to that, but we already talked about it. So, this classical computation is actually just going to be find the GCD and repeat this a few times. Okay, so, because this is such an important algorithm, let us really work out all the details. Okay, so let's first of all set up a little bit of notation. So, here is some notation. For each color C, I will define this indicator function that goes from Zn to 0 1, okay, as Fc of x is equal to 1 if Fx is C and is equal to 0 otherwise. Okay. So, now we had this 1 over root n summation x fx, right, which we got by applying the function oracle. We had this. We rewrite it as So, I will give you a couple of minutes to stare at this. So, I mean not that I did anything much, but basically I am just partitioning this sum over the colors. Okay. So, I will put this indicator function fcx in front of each x. So, this only gets activated when like when we are in a given color, right, and then we just sum over all colors. So, this will just help us in analyzing this. Okay, so let us go forward. Is it fine? All right. So, now first of all one question that we have to answer is what is the probability of measuring a given color. So, it will be 1 over S, but we will just write this down. Okay. So, the probability of measuring a fixed color C summation over x 1 over root n fcx the whole squared, okay, which is 1 over n summation over x fcx. So, why can I get rid of the square? Because this is a 0 1 function. Okay. So, the square and the function are the same. So, is it fine? This is the probability of measuring a fixed color just using the equation that we got, right. So, we're just highlighting this part. Okay. Yeah, and then this is the expected value over x of fcx. This is just by definition of expectation, and this in turn is the probability that fx is equal to c, which is equal to 1 over s. Okay, so it is just a sort of simple implications. Okay, so we just rewrite the term that we have in terms of expectation. So, it just follows by the definition, and then because fcx is a 0 1 function, this in turn becomes just the probability, okay, and which is 1 over s. All right. So, now next what we will do is sort of rewrite the state. So, the state that we have okay. So, now we have our resulting state as okay. So, here this normalizing factor, do not pay much attention to it, I am carrying it around till I can. But basically what we have done, everybody understands, we have measured our second register, we are talking about what happens to the first register, right. So, I mean obviously, so our second register is now collapsing to C, and you are getting a summation over here. So, the reason that I am not restricting the x in the summation to to a particular class is because I have this indicator ahead of it. So, it will work out correctly. Okay, so fine. So, we got this state, and we will in turn rewrite this as 1 over root n summation x in Zn, okay, square root S Fcx x, okay. So, so remember that, you know, once we collapse our second register, we typically just throw it away, right? We do not have any further advantage to gain by that. So, now we consider only the first set of registers, and this is what we get, okay. So, I am just rewriting what we had before. I mean, there is this small reordering that we did, so that this square root S is inside with the Fcx, okay. So, now is when the algorithm really gets interesting, right. So, now this is the stage at which we have to show that applying the QFT makes this you know, makes the resultant state somehow independent of color, right. Everybody agrees with that. So, we have been discussing this. This is the main step. This is the main subtlety of the algorithm. Okay. So, now we apply QFT. Okay. So, now let me just say that I define G as root S Fc, okay, and let 1S be an indicator, a sort of a membership testing function. So, let me define it. So, what this means is that 1S of x will be 1 if x is in S, okay, and otherwise it will be 0. So, this is just a simple membership testing function. So, we are just setting up some notation, right, okay. So far so good, okay, good. So, now as I said, we want to show that essentially whatever you know, whatever we get after applying QFT is independent of the color.